Okay, so now we're ready for the last section of chapter 4 of 4.5, which is something called integration by substitution. Now, it turns out this is going to be a hugely important technique. And so, first we have to introduce it properly and explain where it's coming from. But once you get the hang of this, you'll find that it's going to be enormously helpful. When you try to calculate the solution to an integral, because many of them can be solved this way. So it does require a little bit of cleverness sometimes, but it can work extremely well. So that's why they're showing it to you now, so that when you get to Calc 2, you'll already have that in your background, and then you can focus on the more advanced techniques that they will be teaching you. So what's happening with integration by substitution? Well, in a way, you can think of it as the reverse of the chain rule. Okay, so here's the chain rule. Now, I do want to remind you basically how that works. First, so if you remember correctly, if you're taking the derivative of a composite function, okay, you're going to get f prime of g of x, g prime of x. Okay, so that's the chain rule. So for example, what if we had something like this? So what we have to do here is think of this as our g of x. Okay, so g of x is x squared minus 2x, and then f of x is 3x to the fourth, so that f of g of x is 3 times x squared minus 2x to the fourth, because what you're doing is you're substituting for each x, g of x right there. Okay, and then since f prime of x in this case, based on the power rule, would be 3 times 4 times x to the 4 minus 1, or 12x cubed. And then based on the same rules, g of prime of x will be 2x minus 2. When you plug in the result up here, f prime of g of x, g prime of x, so we're going to have, here's our f prime of x, 12. And because it's f prime of g of x, we're going to replace um, the x with g of x. Okay, and then we still need g prime of x, 2x minus 2. Okay, so again, the chain rule is very, very powerful. We see it quite often, but it does, of course, take a little getting used to. So anyway, so this is the chain rule, but it implies, by the way, that we could do the same thing with an integral. So just keep that in the back of the mind when you see what they're doing here. It works with integrals as well as the original function. Okay, this is a part of the chain rule. They both um, are coming from the same rule, the chain rule. So they both um, could be thought of as two parts of the chain rule. All right. So in other words, you're just replacing all the lowercase f's with capital F's. But um, okay, so that's what they're telling us right here. And then what that implies is that if you integrate the right-hand side here, then we'll have to bring us back to whatever this is. And of course, don't forget the C. So that's where this is coming from. And then what they're going to do is say, well, listen, if you integrate the statement of the chain rule right here, Um, well, actually, no, what they're doing here is something slightly different. If you would, let's run through this again. I think they're not showing it maybe as clearly as they could. Let's start again with the statement of the chain rule, which means that I could do the same thing with the integral. And you can see that it becomes capital F prime of g of x, g prime of x. Okay. And then if I integrate, it brings me back to here. But here's the missing piece, I think. F prime, remember, capital F is the integral. If you take the derivative of that, it brings us back to the original function, which means that capital F prime of g of x would therefore be the same thing as simply f of g of x. Okay, so therefore, what this means is I can rewrite this piece where I'm replacing this piece with this equals therefore the same thing as I see here. Okay. So this is the heart and soul of everything that we're about to do. So what they're going to introduce us to is the idea that we can replace one of these variables with a different variable, which makes the integration simpler. So what if I were to do the following? Suppose I said u is a function of g of x, is g of x, okay? Um, that implies that du dx is g prime of x, and that in turn implies that du is g prime of x dx. So therefore, what you've got here is this becomes f of u, and all of this becomes du. And this becomes f of u plus c. Now, why are we doing this? Because very likely the integral that we are looking at here is much simpler than the one we started out with. Now, of course, when you're done, you have to substitute the definition of u um, to find the answer as a function of x. Now, this all seems very strange at first, but when we do an example, you'll say, oh, I see what you mean. It doesn't look that difficult. So, for example, what if I try this? Now, based on the rules that we know up to this point, this is going to be a nightmare. I mean, I guess we could do it. by expanding that term, but maybe there's a quicker way of doing it. Okay, so why don't we try this? Let's let u be this piece here. Du dx would be 2x, and then du is 2x dx. And then that means this function you're seeing here could be thought of as x squared. Okay, so what that means then is f prime of x would therefore be 2x. So we can rewrite this as not f, no, u. That's the whole point of this. U squared du. Okay, so remember we defined u as x squared plus 1, so this becomes u squared. And we've also shown that if u is x squared plus 1, du is 2x dx. So this equals this. And this is easy to integrate. In fact, we can simply apply the power rule, and we end up with u cubed plus 3 plus c. Now, of course, that's not the right answer because it's in terms of u, but all we have to do is replace the u with x squared plus 1, and we're all set. Oh, well, that's interesting. Huh. Wow. Huh. So this process is called either substitution or often it's called U substitution. And the whole purpose, again, is to simplify the integration from something pretty awful to something much more down to earth with the appropriate switch of variables. But it takes a lot of practice to get used to this kind of thing. You know, after a while, you'll notice right away what you're supposed to do. If you make the wrong choices, you'll end up with a bigger mess on your hands and you'll know right away. So, this way, I think you'll agree that this integral is quite a bit simpler than this one. Not that we couldn't have done it, but it would have taken a while compared to this one. And so that's what this is all about. Okay. So let's see what they've got for us. And then here again, they're just showing you what I just showed you. Ah, here's one. Um, oh, is that the same one I just did? Yes, it is. All right, let's do a different one. Let's try, oh, here's some we can do. So now, usually, what you're going to, after a while, you get a feel for this. But in a case like this, because I've got an exponent, I'm going to try to let this be u, and let's see what happens. Then du dx is 2x, or du is 2x dx, which we do have. It's just that it's not in the right order, but there it is. And then that would imply that our function is x to the fourth. And the derivative of that, of course, using the power rule for derivatives, is 4x cubed. Okay, so now remember, first thing we're going to do is rewrite this as, yes, just be aware that, you can just move these around. So they don't have to be next to each other, but it's easier to see that those two combined give us du. So, of course, we know how to handle this one. It's very simple. And of course, then we substitute back the definition of u. And that's it, we're done. And if you don't believe it, or if you just want to double check, you can take the derivative of this function, given that the derivative of c is 0, and that will bring you right back here. In fact, if you're going to use the chain rule, and when you use the chain rule, it'll bring you back to the original function. How about this one? All right, so you're starting to see a pattern here. The u should usually, if you're looking at polynomials of some kind, the u should probably be the one that contains the highest exponent, so that when you take the derivative, you'll hopefully end up with the u in your expression. Okay, so let's try it here. Okay, and then that would imply that f of x must be the square root of x. Okay, so therefore we have, if you want, we can rewrite it a little. So we have the integral of radical u du, or u to the 1/2, and based on the power rule, we're going to have u to the 3/2 over 3/2 plus c. First, let's simplify it a little. And remember, u at some point we defined to be x cubed plus 1. And that's our final answer. Okay. And again, if you're not sure, you can double check. You'll need to use the chain rule, but you can certainly confirm it by using the chain rule, and it will bring you back to the original function that we had. Square root of x cubed plus 1 times 3x squared. All right, so we're in a roll now. What else did they have for us? Ah, trig functions. Okay. Um, so I don't have a chart right in front of me with the basic trig derivatives. Let's see if we can get a hold of one. You know what? We can go right back to I think Brightspace is open. If not, well, I mean I can go look it up. I've got a table here somewhere that I posted, which has all of these wonderful formulas. I just forgot to open it up. There we go. Um, Rules of differentiation, beautiful. So let's see if there's a, here we go. Now the derivative of the secant is the secant times the tangent. I don't think that's what we have, but we do have the tangent. Oh, I think we have what we're looking for. Here we see that the derivative of the tangent equals secant squared x. So therefore, let's see what happens if we allow u to be tan x plus 3. Now, of course, the derivative of a constant is zero. So we're going to have this piece plus this piece represent du. So we're going to have u du. Oh my God, it can't be that easy, can it? All right. Okay. Now that one's trickier because, of course, the trig derivatives, it takes time to remember them all. Um, all right. Anyway, so what else do they have for us? Oh, okay. Now sometimes we don't have exactly what we need to pull off this U substitution, but we might be able to rearrange what we do have algebraically. Like here, for example, if we try U to be x squared plus 1, that would imply that f of x is x to the 4. So yeah, here's the problem. Du is 2x dx. We don't have that, do we? Let's first rearrange it. What do we do? All right, so because we're only missing a constant, we can actually supply it ourselves. Watch how this works. We didn't change anything. We were dividing and multiplying by 2. And so now all of a sudden, look how convenient this is. This one is u to the 4th, and this is du. And then we, of course, make the substitution. 1 over 2 times 1 over 5, of course, is 1/10. And that's it. We're done. And so this one, you might have thought, well, we're stuck here. We don't have what we need, but we can provide it ourselves. Okay, it's not always going to work out this way, but sometimes if we're just missing a constant, that means it's very straightforward to turn it into a form that we can apply our rules to. I think they have another one here, which is exactly the same thing. Yeah. So let's say again, we let u be x cubed plus 1 because we're looking for the highest exponent. Don't let this be x. You rather, because when you take the derivative, the exponent will actually go down rather than up. So always start with the highest exponent if you're not sure. Bad luck. We don't quite have what we need. But guess what? Since we're only missing the constant, we can supply it ourselves. So we've got 1/3. Whoops. Remember, this is du. Great. And of course, you notice I wrote the square root as 1/2. Now, of course, dividing by 2/3 is the same as multiplying by two, sorry, divided by 3/2 is the same thing as multiplying by the inverse, which is 2/3. So I've got 2/9 u to the 3/2 plus c. And of course, u is x cubed plus 1. All right. So let's see. Now, I think, oh, yeah. All right. I think we've got enough of these done. Let's try this one. Ah, very good. Let's try this one. What was it again? I copied it. So we'll try u x squared plus 1. And we don't have that. Well, we're close. We just needed 2. Not a problem. This will be our du, and this is our u. So we end up with based on the power rule, and then we'll end up with u cubed over 6 plus c. And of course, u, we chose to define it as x plus squared plus 1. And there we go. All right. So after you do like 100 of them, it'll start to become second nature. Okay. Because, all right, now change of variables for indefinite integrals. So that's, basically what they're building up to here. All right, so let's look at this one. All right, so let's try u, 2x minus 1, du dx is 2. All right, so again, we're almost there. And that means we have u to the 1/2 du. And so that's going to give us u, of course, is 2x minus 1. And then we're all set. And I mean, you can see that this, if we didn't know about this, this would have been quite the nightmare, I think you'll agree, because it's just not related to the basic rules that we know. But once we know how to replace it with something more manageable, that makes all the difference in the world. All right, what are they? So they're going to also remind us, I mean, they're just telling us what we were just doing. Now, we know the power rule for integration. which is, but now they're going to introduce what they're going to call the general power rule, is a little bit more complicated. And here, what's happening is that, all right, let's just copy what they have here. And so you can see the difference is that up here, we simply have x to the n. Here, it's g of x to the n. Okay. And so this is the extra part. So what you're effectively doing then is again integrating from the chain rule. And so this is what we end up with. But now here is where it gets interesting. If this part is missing or any part of it is missing, unless it's a constant, we can't just supply what we're missing, only with constants. If it's something else, then we might have to try a different rule. Okay, so let's see what example they have for us now. Oh, we got quite a few examples. All right, let's try one of these. 3, 3x minus 1 to the fourth. So we can move the 3 outside. Now here, what they're actually doing is, no, they are using the U substitution. Okay. Um, so du dx is 3. And then, of course, that means that du is 3 dx, which we actually do have. I just realized I probably shouldn't have moved it out there. So here's what we've got. So think of this as u to the fourth du. And of course, u is just 3x minus 1. And that's it. We're done. Wow. Not bad. What's next? All right. Ooh, this one looks, yeah, some of these, they start to look familiar after a while. I think, yeah. All right. Well, all right. We'll try them anyway. Even if we've done similar ones or even the same ones, we'll do it one more time just to get some practice. Here we have 2x plus 1, x squared plus x. Oh, that's it. Okay. Ooh, well, now this one might be a little trickier, but let's try. So again, you should usually try, if you're not sure, pick for your u, pick whichever expression has the higher exponent. Chances are that will be the correct answer. Well, here we got lucky, but that's for sure. Because these two give us du. If you just rearrange it slightly. And over here, it's just plain u. Okay. And then let's try this third one. Yeah, it looks kind of familiar, but all right, that's okay. X cubed minus 2. All right, so once again, we're looking for the highest exponent, even if it's under a square root sign. Okay, so we do have what we need. We just rearrange it slightly. This is our du. U is under the square root sign, so we have so that of course is the same thing as multiplying by 2/3. And here we have x cubed minus 2 to the 3/2 plus c. Yeah. Okay. All right. Oh, there's more. Oh, okay. All right. Let's try this one. Integral negative 4x over 1 minus 2x squared squared. So let's try u equals here. All right. So this is equivalent to du over u squared, which I'll rewrite as u to the minus 2, of course, to make it easier to apply the power rule. We might, in this case, we might want to rewrite it as negative 1 over u, make it a little simpler. And of course, is 1 minus 2x squared. You know, 1 minus 2x squared. And there we are. Now, this one, well, we have to be careful. Oh, no, we don't. You know why? Because one of these is squared and one is not. So therefore, let's try u is cosine square of x. Ah, no, they don't want that. They're suggesting that we try this instead. Yeah, this makes sense because the derivative of the cosine is the negative sign, which we don't have, by the way. We don't have that negative. That's all right. We can supply it. So here's what we need to do. There we go. So we haven't changed anything. This is correct. This becomes our du, and this can be thought of as u squared now. Okay, if u is cosine x, then then u squared is here, and then we have du, so we have minus plus c. And of course, now we make the substitution back to whatever u was, cosine x. And of course, plus c. All right. Now, here's an interesting, now, where are they going with this next part? What they're saying here is this. We can use substitution for definite integrals as well as indefinite integrals. Of course, up to this point, we've only used indefinite integrals, the ones where you do not solve for a specific value. Does anything change when we use it for definite integrals? And the answer is yes. There's one very important change. The limits are the limits of integration must be changed to reflect the definition of U. All right, so we'll see what that means in a second. And here's the formal way of writing that. Now, again, it's going to be hard to visualize what this means until you actually do it once or twice. What they're saying is if you're going to integrate um, U instead of f of g of x, you can't just leave the lower and the upper limit of integration the same because they refer to x and we're dealing with U. So what you have to do is change the limits of integration as such. All right. So let's try one of these. Okay. So in other words, you have to change those limits of integration. Otherwise, you'll get the wrong answer. All right. Let's try this one. So we'll use U substitution. This one is a pretty straightforward one. It's not much different than the ones we've seen up to this point. We don't have the 2x, but we can provide it. By multiplying and dividing by 2. And so here we have our du. And here we have, oh, I left out the 3, sorry. That would help. U cubed. Now, here's where we have to watch it. We decided to let U be x squared plus 1. So the upper and lower limits can't stay here at 0 and 1. Here's what we're going to do instead. So first, keep in mind that U is actually a function of x. So if we write it like this, they'll help us understand what we have to do. We need to evaluate U at 0, and then we need to evaluate it at 1. And then now the integral, the definite integral, is going to look like this. Wait, sorry, it's U cubed. It becomes U to the 4th over 4. Oh, by the power rule, that is. But the limits of integration are not 0 and 1. They're now 1 and 2. So that's really the big change. Okay, so then we're going to have 1/8. And then we have 15 over 8. Okay. And that's our final answer. All right, so they're mentioning it here too in blue. They're changing those limits um, to two, one and two, because now we're integrating u instead of x, and then we'll end up with the correct answer. That's the only tricky part when you're using u substitution for definite integrals as opposed to indefinite integrals. All right. So we have odd and even. Let's see. So here's some important results that we want to know. First, you might remember from your travels, what does it mean to be an even or an odd function? For all x in the domain. So the classic example of this would be, oops, let's try that again. Y equals x squared is an even function because f of 2, for example, would be 2 squared, which is 4, but f of negative 2 will be negative 2 squared, which is also 4. That'll be true for every x. Um, whatever x is, f of x equals f of negative x, regardless of what value it is. That makes it even. Odd means this. Ah, okay. So the classic example of this would be y equals x cubed. So for example, if x is 2, f of x is 8. If x is negative 2, wait, hold on, let me draw this in here. Instead of equaling 8, it'll be the negative of that. So in other words, 2 and 8, if 2 and 8 are on the point 2, 8 is on this function, then we must also have negative 2, negative 8. Okay, so that's what it means to be odd. Okay, and by the way, if you notice, one of the implications of this is that here we have symmetry with respect to the vertical axis, meaning the left and right hand sides are mirror images of each other. And with odd functions, the symmetry is with respect to the origin. And that means that either the first and the third quadrants are mirror images of each other, or else the second and the fourth. Okay, anyway, so what they're telling us here is that with all that being said, these rules apply. If f is even, then um, this integral is the same thing as 2 times just the positive part. So in other words, if we had something like this, the entire area there, let's call this, I don't know, 1 and 2. 1 plus 2 equals 2 times 2. Okay, that's what it's trying to tell us. And if f is odd, then the same integral will give us 0. So let's take a look at that last function and see why. Sorry, this is positive 2. So if I decide to call this area 1 and 2 again, now remember, when you're under the horizontal axis, the area is negative. So that means that 1 is negative pi 2, which means that their sum is 0. Huh. We mentioned this earlier, but with an odd function, the sum is going to exactly equal 0. So we can't interpret it as you know, a total area. But what we do know is that that's because half of it is positive and half of it is negative. All right. So with that being said, let's see what they've got here. Oh, wait, they've got a nice little graph here. So let's take a look at this. Sine cubed x cosine x plus sine x cosine x. You can see from the graph, it's an odd function. And therefore, between negative and positive pi over 2, this area is the negative of this area, and they add up to 0. All right, so there's a couple of practice problems here. We may as well take a look at them. All right, we'll start with this one. So again, as always, we want the higher exponent involved with our u definition. So we'll let that be there. Du dx. Oh, actually, here they've changed it to t, those clever guys. Um, it makes no real difference which one is the independent variable. So it's going to be 5t to the fourth, or du is 5t to the fourth dt. And we almost have that. We're close. So, well, first let's rewrite it. And then, you can see that we'd like to have 5t to the fourth. We don't have it, so we will supply it ourselves, which we're certainly allowed to do by both multiplying and dividing by 5. Actually, no, sorry. I want 1/5 over here. All right, now we're getting somewhere. So this is of course du, and we have using the power rule, we have 1/20th u to the fourth plus c. And of course, u is t to the fifth plus 4. All right. Then which one is that? That looks like it's B. Yes, it is. Okay. Now here we got a mess on our hands. But keep in mind that general rule was that always try to let u represent the term with the highest exponent. So let's see if that works here. All right, so we're actually in pretty good shape. We just need to supply a negative. So the numerator here is our du. And down here we have u cubed. All right, well, that won't be too bad. So rewrite it as u to the minus third, and the power rule tells us this is going to be u to the negative 2 over negative 2. Plus, of course, the c. And we'll have, sorry, u is cosine of x. You know what? Let's tell it. Let's write it like this. Oh, I just didn't even realize there's two negatives there. All right. 1 over um, u squared. That should do it. Yeah, so it's a. Oh, wait a minute. What happened to that two? Oh, I lost the two. That's why. Sorry. Yeah, we're good. Okay, that's the end of that. That's A, and we're done. So, boy, that was quite intense, wasn't it? But now you are in possession of an incredibly powerful technique for doing integration. Use substitution. You'll see it all the time as you go forward. So it's good to get practice with it now. Okay, so now that's that. Now, five. Um, we're going to introduce functions that we haven't really focused on up to this point, specifically logarithmic functions and exponential functions, because they're awfully, awfully important and they're used quite a bit in calculus. So we'll be bringing those in and combining them with the techniques that we already know in chapter 5. So we'll start that next time, and I'll see you then.